Hello, everybody. We are the FTC team 14779 Spontaneous Construction. I'm Aaron, a member of our team's software team.
I'm Ian, I'm the hardware team lead.
I'm Derek, member of the hardware team.
I'm Jackie, I'm on the hardware team.
And I'm Leah, I'm on the hardware team. So Jackie and I will be monitoring the Q&A section, so feel free to put any of your questions there as we're going through the presentation, and we'll make sure we get to those at the end. We will also be recording this presentation, and the video as well as the slide deck will be available on our website later today.
Yeah, cool. All right. First, I'm going to go over what we're going to talk about during this webinar. Initially, we'll start with talking about who we are, what we built for this year, talking about Swerve, that kind of thing. And then second, we'll be defining what Swerve is for those who don't know that much about it. The third, we'll go over the different types of Swerve, specifically coaxial and differential. In the fourth, we'll do a comparison between the two of those. Then we'll talk about what we learned in terms of the hardware. Then we're going to talk about the software side, so programming it from beginning to end in the tally-up period, as well as some of the autonomous stuff. And then we'll end off with additional resources for both Swerve and just general FTC stuff. Yeah, and as Leah said earlier, if you have any questions, put them in the Q&A area, and we'll be recording this presentation and uploading both it and the presentation itself onto our website later today. All right, let's get started. Okay, sorry. Yeah, so a bit about who we are. We are a fifth-year FTC team from Minnesota, and during this year, we actually won First Inspire at the Minnesota State Championship. So we're going to be heading to Worlds. If any of you guys are also going to Worlds, feel free to come visit us in the pits. This will be our first time at Worlds, so we're going to be trying to meet as many people as possible. So it's going to be really fun to meet some of you guys there. Last year at the Chicago Robotics Invitational, we actually drove a Kiwi drive there. So we have a history of working with sort of unique drive systems, to say the least. And during this season, we actually used a 4-pod differential Swerve drive, and we're still going to be bringing it to the World Championship in April.
Now let's move into what is a Swerve drive. Simply, it is a drivetrain that has multiple pods that are able to rotate independently of each other. And a pod is the central rotating part that contains the wheels and all the gears necessary to rotate and move that wheel. And the total movement of the drivetrain is a combination of all the pod's rotations and powers when it's running. And there are two main types of Swerve drives, coaxial and differential. In this presentation, we'll be referencing different parts of the drivetrain. The first one is the Swerve module, and that's the complete self-contained unit that contains the rotating pod and all the motors and gears required to run that. Pod, as I just mentioned, is the central part of it that contains the gears and the wheel. And the structure is the part inside of the pod that everything is mounted to. So why should you use Swerve? The main reason to use Swerve is because it's so innovative. Since it's very uncommon, there's a lot of room for innovation and different designs you can do with it. We're also going to compare it a lot to Mechnum, since Mechnum is the main drivetrain that most teams use. Swerve is going to typically be stronger since it uses stealth wheels and those have a higher friction. It's more complex and more innovative. It has a better defense since it's a lot harder to move, and it's also very reliable. Mechnum, however, responds a lot faster to inputs because it doesn't have to wait for pods to rotate to face the right direction. It's a lot easier to design. It's more versatile, and since it's the most common design, that means there are a lot of resources out there for it. While Swerve does have a lot of good things, there are also a couple reasons not to use it. First one is that it takes a lot of time to get right. A lot of teams have to use the entirety of the off-season to properly design and refine their Swerve drive to get it to a competitive level. It can also cost a lot more than a normal drivetrain to produce and refine, since you'll have to use almost all completely custom parts. And because of this, you'll run into unique challenges specific to your own drivetrain. Since it requires all custom parts, it also requires a lot of advanced CAD skills. And not all games are suited for Swerve. An example of this would actually be this year, since it requires a lot of tight turns and precision that are played in the field. And this isn't exactly suited for a Swerve drive. And we don't recommend inexperienced teams use Swerve for their first year.
So what are the different types of Swerve drives? There are two main types, coaxial and differential. With coaxial, it has one motor for rotating the pod and one motor for rotating the wheel. Differential has the two motors working together to rotate the pod and the wheel. Starting off with coaxial Swerve. How does it work? Well, one DC motor rotates the wheel. The rotation of the motor goes through a chain of gears that ends up going to the wheel gear. And another motor rotates the pod. This motor doesn't necessarily have to be a DC motor and can actually be done by a servo. In the diagram, you can see the rotation motor is the yellow motor and how it rotates the entire pod on that central axis. And while the black motor is the drive motor, it goes through a series of the other gears and bevel gears that ends up rotating the wheel. So attaching a pod to the drivetrain. Personally, we don't have as much experience with coaxial, but similar concepts apply. So for considerations on where to place the pod, you have to keep in mind of the gear sizes that you're going to use, the wheel diameter, and the motor size, as well as where you're placing the motors. And because how complicated a swerve pod can be, you'll most likely need a custom base plate. This is because holes may not align with standardized parts such as Tetrix C-channels. And when making a custom base plate, keep in mind of the thickness. For us, we used aluminum because you can also make it thin and hard, but you can use other materials as long as it suits your needs.
Now let's move into talking about differential swerve. In this section, we're going to be referencing our own swerve a lot here. So here's a diagram of one of our swerve modules. In it, we have two motors which power an upper and lower set of gears. These gears connect directly to a gear which we call the bevel gear, which connects directly to the wheel in the middle of the pod. The upper gear has a ring of supports around it to make sure it doesn't move at all and doesn't wobble side to side. These supports are connected to an upper plate. So how does a differential swerve module work? As I mentioned, there's an upper and lower set of gears, and depending on how these rotate, it either, if they rotate together in the same direction, it rotates the entire pod, but if they rotate in different directions, it rotates the wheel in the middle because of the bevel gear. And variations between the motor speeds, variations between the motor speeds allows rotation while moving the wheel in the middle. As you can see here, when the motors move in opposite directions, it rotates the wheel in the middle, but when they move in the same direction, it rotates the wheel side to side. So here's a exploded view of our swerve pod. Inside of it, we have a metal superstructure which connects to two rev bearing blocks. We have a metal superstructure because we want all the weight going from metal to metal contact to ensure that no damage happens to the swerve structure inside of it, as that holds all the parts that actually runs the swerve pod. We also have a groove inside of the upper and lower gears, which connects to a V bearing, which makes sure the gears don't move like side to side or pop out of from where they're supposed to be.
Now for some comparison between the two. So why would you use coaxial? Well, the benefits that are that they are easier to understand and simpler to program. This is due to the fact that the two motors are separate from each other, as one rotates the wheel and one does rotation of the whole pod. And you can also use servos for rotation, which allows DC motors to be used for other subsystems, and it also leaves encoder ports open for other things such as odometry. However, it is less powerful than differential as there's only one motor rotating the wheel, and it usually requires the use of extra belts, chains, or gears. And it also usually takes up more vertical space as you have the gears above the wheel.
For differential, it's going to be twice as strong as a coaxial because it uses twice as many motors. It's also very reliable and can have a smaller vertical profile, and you don't have to use belts or chains. However, since it's so complex, that makes it a lot harder to both build and program. If you're using a 4-pod differential swerve, it'll use all 8 of your DC motors and encoders, which means you can't use dead wheel odometry to track where your robot is. Also, it'll use a lot more power, which means it'll drain the battery very quickly.
So what did we learn throughout our journey of making our swerve? One of the challenges that we ran when designing our pods is how to attach it to the drivetrain. You see, because there's only one mounting point for the pod, this is due to the fact that the pod needs to rotate around a central axis. So we used a custom base plate for the pivot holes, and we also used thrust bearings to take up between the vertical plate to reduce the wobble. We used a central bolt as the pivot point, and we used nuts to clamp it in place. We also used herringbone gears to help with self-alignment. This is due to the fact that the V shape of the herringbone gears help the gears channel through each other. We also use rails and support gears to hold in the pod. In the pictures, you can see how the support gears hold it in and how the bolts and nuts clamp down on the thrust bearings, which are pink in this case, and that prevents any side-to-side wobble. Because the entire weight of the drivetrain rests on those pods, you'll need bearings in order to have smooth rotation movement. And the two bearings you can use are thrust ball bearings or needle bearings. So for thrust ball bearings, there are ball bearings between two grooved rings. The benefit of this is that they're self-aligning because the balls can't escape the grooves, but they're more expensive for larger sizes. Another option, which we ended up using, was needle bearings. They are made up of needle rollers that are sandwiched between two flat washers. They are cheaper for larger sizes, however, you'll need guides to align them, because in the cross section, as you can see, the black section is the needle roller, and there's no grooves to hold it in place. This means that any side-to-side movement can cause them to slide past each other, and your bearing won't be a bearing anymore. You'll need guides, which in this case are purple, to make sure that they're in place. So how did we design our pod? We used a software called Fusion 360 for our CAD work. It's a free program and everything is stored in the cloud. We first worked out the spaces that we had and the wheel sizes that we were going to use. And we started from basic working prototypes and built up from there. We also did lots of extensive testing to make sure everything works as it should. And if we ran into any specific problems, we would contact local engineers to help them, to let them help us. And we also document what went well and what to improve in the future. In the photos, you can see how a bevel gear is being made and also a plug-in feature for making a spur gear. So the types of gears, there are two main types of gears. There are spur/herringbone gears and the bevel gears. So for the spur/herringbone gears, what is the difference? Well, spur gears are pretty simple to make. They are straight tooth channels. So that means you can slide them against each other for easy assembly. And herringbone gears are these V-shaped tooth profiles. And what these V-shaped profiles do is that they can help with the center alignment and help with more force from the motor to the actual rotation of the pod. And keep in mind that the ratio of the pod turning versus the wheel turning are different. In most cases, they're kind of flipped, because when the drive gear rotates the wheel, you can see how the drive gear is bigger than the bevel gear, which means think of it like a 2-to-1 gear ratio. However, or 1-to-2 gear ratio, sorry. However, if it wants to rotate the pod, then it's a smaller drive gear rotating the big ring gear, and that will give a slower rotation speed. This is important because the ratios affect robot tracking. If you're going with all 4-pod swerve, that means all of your encoder parts are used up by the motors. So you'll have to keep in mind of the gear ratios. And also, it's a good practice to use odd gear ratios, such as 21-to-10. This may sound a bit weird, but this is because as the teeth wear down, you don't want the same teeth to wear each other out over time. You want the teeth to wear down evenly throughout a different set of teeth each time. And for bevel gears, they might be difficult to CAD, so it's always helpful to look for tutorials on how to make them. And keep in mind that the size of the middle bevel gear affects the amount of ground clearance you have from the bottom of the wheel to the bottom ring gear. For gear parameters, when you create a gear let's say from a plugin, there are many different types of parameters that you can change. While there isn't a one-size-fits-all and many values can be changed, don't focus too hard on these values. So some parameters might be confusing, and here are some simplified definitions for each parameter. So for gear module, that's essentially how big or how small the gear is. If you go a module that's too small, let's say 0.5 millimeters, then you run into issues of the gear stripping if you exert too much force on them. However, if you go too big, let's say a 5-millimeter module, then you will have a hard time with the motor trying to rotate the pod, and you might not have enough room for mounting. We chose 2 millimeters as we found that was a good balance between those two. If you're going with herringbone gears, a helix angle is also another parameter you can change. That's essentially the angle of the gears from the vertical. If you choose too high, then the angle will be more slanted. And then you might run into the issue of installing them because they can't slide past each other like spur gears. If the angle is too high, it might be physically impossible to install them to your drivetrain. And if they're too low, then you just essentially have a spur gear and you lose the effect of the self-alignment. Ours is 15 degrees, as we also found that to be pretty good. Another thing to keep in mind is pressure angle, and that's essentially the force between the two gears. Simplified, it's the higher the pressure angle is the higher the tooth strength. However, that will increase your gear wear and the amount of noise it will make. 20 degrees is a really good balance, as that is pretty standard for all types of gears. And the distance between two gears is also important. You want to make sure that the gears are not clipping to each other, or they're so far apart that they don't actually interact with each other. And that's a very simple equation. It's essentially the sum of the two gears diameters divided by 2. As you can see in the bottom right photo, there it is. You can see the diameters of those two circles. And then distance A is essentially the distance between them from the center point.
As we mentioned previously, a swerve drive is very complex. This is because it requires a lot of parts that have to work together seamlessly. So when you're designing it, you have to remember to allocate enough time for both the design and actually building it. If you run into issues during the design process or when you're building it, it can also be very helpful to talk to engineers, so they have a lot of experience. It's also important to remember how long it takes to repair a pod, as we've actually had an instance during competition where one of our pods is broken and we had to repair it under a time constraint. Also, as we mentioned before, since it's so complex, most teams create their drivetrain during the off-season. It's also important to keep in mind how much space the pods will take up, as all the gears, bearings, and screws will take up their own space. And while cramming everything together as compact as possible might seem like a good idea, in the long run, it can make it a lot more difficult to clean and repair. Another thing to keep in mind is keeping your gears protected. When we were originally building our swerve drive, there was an instance where outside debris fell into the gears and actually broke one of them off. So to prevent that from happening, we added a shell around them to stop anything from getting inside. When we were building our swerve drive, we used 3 main types of plastic. PLA, which is the cheapest, and we use for more general parts, since it's hard, but it's a bit brittle, so it can break easily. We also use PETG, which we use for more structural parts. It's a bit more expensive, but it's a lot stronger and a bit softer, but can handle a lot more stress. And we actually originally used these in our gears, and they worked really well. Eventually, we decided to upgrade these to nylon gears because they are very low friction and high durability. However, they are also more expensive. While we do use a 4-pod differential swerve, there are a lot of other variations on this. You can use a 2 or 3-pod swerve, or even like 5 or 6 pods. However, we don't recommend only using 1 pod because this would prevent you from being able to turn your robot. You can also change the motor placement to be either vertical or horizontal, and you can use belts or more gears to increase the gear ratio or move your motors further away from your pods. An example of a drivetrain not like ours is gluten-free swerve drive, and because they only use 2 pods and they have their motors horizontal instead of vertical like ours.
Okay, and now for the programming behind a swerve drive. Before I go into this section, I want to go over some basic math terminology in case you guys aren't aware of what they mean. First of all, the term delta, which just means to change something. So if I say like delta position, that refers to the change in position of like a wheel or robot or anything like that. Additionally, there's a concept of a vector, which is just a value that represents a direction and a magnitude of some sort. So a really good use case of that is having a velocity vector. So like on the right side here, this robot you can tell is going very fast because the vector is very long, and because of the direction of the area, you can figure out which direction the robot's facing in. This is really useful for demonstrating the logic behind the swerve drive. So it's good to recognize what these mean. Before programming a swerve drive, there are a couple of things you should really be familiar with. First of all, basic drivetrain controls, like how you take an X and Y input from a joystick and convert it into a mechanism input, for example, is really useful because those drivetrain controls can be reused for basically any sort of drivetrain in FTC, and of course that helps a lot with learning swerve drive controls. Additionally, you should be familiar with what a PID controller is. If you don't know, it's essentially a math equation that allows you to determine how much power you need to get a system from one point to another. A good way to use this is for like an arm, or in our case, the angle of the swerve pod. Additionally, you should know what inverse kinematics are, or IK. Inverse kinematics is the math you can use to get or to go from an X and Y coordinate or some sort of like math value to to the positions of certain components of the robot. So for example, a lot of people will use IK to guide a robot arm where it has multiple joints that need to be moved to go to a specific coordinate in space. In our case, it's going to be the angle of the swerve pod. Additionally, you should have some experience using Java libraries for FDC. It isn't actually necessary for programming a swerve drive, but we use a library to do the kinematics for us, which is a very helpful and made a lot easier to do in a quick fashion since we had to do this during the season. Basically, all these concepts and many more are available on a website called Control All FDC, which is a super useful resource for learning about control theory and its relation to FDC. So if you don't know a whole lot about FDC software, or you want to just learn more and figure out what you can be doing better about your robot, I recommend checking that website out and giving it a quick read through. Okay, so here's the layout I'm going to go with. First of all, we take joystick inputs or autonomous commands, which would basically just be the form of X and Y inputs and a rotation input. Then send that to a drivetrain class. The drivetrain class will then solve for the angle and power of each pod based on the position of the pod physically on the robot, and then send that angle and power required to each pod in their own instance of the same class. Each one of these pods will then take in the angle and power, do some math to figure out what motor inputs need to happen to make the pod turn in that way, and then send those motor powers to the motor itself in the commands. So we'll basically be working from left to right with this presentation. First of all, some clarification with the controller inputs. I'm going to be using the left stick Y-axis for your forwards and backwards movement on the drivetrain, your left stick X movements for your horizontal movements, and your right stick X for rotation. This is a generally used for a lot of omni drives like Mechanism or like holonomic drive. So this is just kind of the basic one. This does not include field-centric drive, as that's sort of a different thing. Okay, so how do you convert from an X, Y, and R input into the drivetrain inputs? To do this, we're going to use inverse kinematics, like I mentioned earlier, which is just the math that converts the joystick inputs into pod headings and powers. A good rule of thumb for solving inverse kinematics in any system is to think about moving a whole system in one direction and what each component of the system needs to do to make that movement in some way. In our case, for example, we can think about if the entire robot drivetrain was moving horizontally, what angle would the pods need to be at and what speeds would they need to move at? It turns out that with any swerve drive, for any lateral movements without rotation, all four pods just need to be facing the exact same direction and running at the same speed, which is very convenient because, as you see in the video, it's very simple, and we can directly map the joystick inputs from the joystick onto each pod like so. The rotation input is where it gets more complicated because for a robot to rotate while sitting completely still, remember, just imagine one dimension, in this case, the dimension of rotation. In that single dimension, all four pods need to be facing different 45-degree increments and then be rotating clockwise depending on where they are so that the whole robot can rotate in one direction. Because of this, when we're mapping the R joystick input onto each pod, they'll be different depending on the position of the pod. In our case, with 4 swerve pods, the actual R inputs will look like this. And a general rule of thumb for figuring out what the R input mapping would look like is that if you have a center of rotation, so the very center between all your pods, and you drew a line from that to the swerve pod's location, it would be 90 degrees off to the right of that, so that a positive input would bring a clockwise rotation. Here's an example of how we'd actually use this. Let's say, for example, the robot wants to move forwards and to the left while turning to the right. The driver would input a movement looks like this, where the left stick goes up to the left and push the right stick to the right. And then we can start by mapping out the left stick. So the X input would be small and slightly to the left, which we map to each pod as shown here. And then the Y input would be much larger vertically as shown here. Then we map the R input, which is fairly large going to the right. And so each pod will get a fairly large R input like this. And then we want to average out the 3 vectors for each pod. So when you take the 3 vectors and average them out, you'll get a net vector, which is shown in blue for each one of these pods. This will basically give us a certain target velocity. So for the top left pod, for example, it's 2.6 meters a second. And then since they're all vectors and we have headings we can average out, we would also get a target heading, in this case, 30 degrees for the top left pod. This is really effective for creating the actual swerve drive like movement and is good in a perfect world. But there's one issue that we need to cover before moving on from this. Oh, well, actually, before that, this is all the step-by-step instructions on the left again. I'm not going to go over it, but later on, if you want to come back to it, you can read this again to understand the process once more. So here's the issue with the drivetrain I was talking about earlier. Let's say this bottom left pod got an assigned speed of 3.2 meters a second, but since our robot isn't perfect and can't travel at infinite speeds, it actually has a maximum speed of only 2.8 meters a second. If we tell the pod to move at 3.2 meters a second, it's actually only going to move at 2.8 in the real world because, of course, it can't go faster than the real limit. If this happens and we just let it go like such, then the back left pod will be running slower than it should be, and it will cause all the other ones to drag, to basically be dragging it and pushing against the ground, which will cause a lot of field damage, as well as causing a lot of damage to your gears and the actual motors themselves. It'll even drain your battery super, super fast, which is just generally not a good thing. A good way to solve this is called normalizing the wheel speeds. Basically, what we're doing is we find the ratio between the highest assigned speed and the maximum speed possible and reduce it down until it's equal to the max speed. And then we use that ratio and apply it to every other pod as well. So, for example, if this one's reduced from 3.2 to 2.8, then the top left pod would go from 2.6 to 2.1. This isn't a super complicated thing to implement, actually, since you can just use this equation right here to apply to each of them. Basically just assigning the speed times the ratio between the max speed and the highest speed, and just using that for your velocity rather than the initially given velocity from the drivetrain equations. Using this, it'll make your driving much more efficient and also will be a lot cleaner. So, of course, I recommend trying this out. Okay, so what does the code actually look like? In our program, we use the FTC lib, which is a pre-made library which does a lot of different things for FTC, including PID controllers and mechanism drivetrain stuff. In our case, we're using the Swerve Drive kinematics class, which exists inside the FTC lib. The way we use it is we first create an array representing each pod, which will be used later. Then we create 4 new pods with translation 2Ds. This translation 2D will allow us to assign the actual position of the pod on the robot, which of course, as I mentioned earlier, is used for the angle of the rotation axis. And then once we have those 4 pods assigned, we create a new Swerve Drive kinematics class that has the 4 pods inside of it. Now, one thing to know about the FTC lib before we continue is that the FTC lib Swerve stuff, I believe, is actually a work in progress. I remember hearing about that somewhere, that it is hasn't been tested a whole lot. So if you are going to use the FTC lib Swerve stuff, I recommend giving it a lot more testing to make sure it works in all of your situations. Because if you implement it in certain different ways, maybe less pods, more pods, or pods that are further away, it might lead to issues. Again, I don't know for sure if it is still work in progress, but I have heard that in the past from other people who have worked on FTC Swerve stuff. Okay, so once we have it initialized, here's how we actually move it. In our case, we use a movement method that takes in the X, Y, and R input. So like the ones I showed earlier on the controller. Once we take in those 3 inputs, we assign them to a chassis speed, which is an FTC lib item that basically represents the speed of the robot we want. And then we can take that chassis speed and input it into a dot to swerve module space method, which will modify the module states array we made earlier and basically assign a speed and velocity to each one of them. Then this line of code right here will normalize the wheel speeds as we showed earlier. In our case, we're using a 1.2 meters a second as a maximum speed. We haven't actually had time to test what would be the optimal for our drivetrain, but depending on which drivetrain you're using, that value will be different. So testing to solve for that value is very important. And then after that, we assign the actual speed and velocity to each one of the 4 pods. In our case, the module states array here, where we call one specific part of it, being front left, front right, or etc., is actually going to give the heading and velocity of each pod that they need to travel at. The power factor parameter we have here is a speed modifier we've used for all of our drivetrains, where it basically multiplies the final velocity by the power factor. You don't really need to use that if you don't want to, but that's just so you know, all of the heading, the target angle velocity stuff is happening in the module states part of this method. Okay, so now we have sent to each pod the target heading and the target wheel velocity. What logic goes behind actually making the pod move at that angle and power? First of all, we can use a PID controller to control the heading of it. So basically just saying the R power, which is the value we'll use to represent the power needed for rotation, saying that to a PID controller, which will take in the angle or basically the error to turn to the left to face the target. And then we tell it to move if it's close out to the target. If you left this part out, the pod will immediately start moving forwards, even if it's not facing the right direction, which is an issue because it'll lead the pod to go in a sort of drifting motion like that, rather than turning and then moving forwards. So that'll kind of confuse the actual position of the drivetrain. The way we account for that is we have this if statement that says that if the angle for the target, basically the error, is larger than a certain margin of error we assigned, in our case, I think it's like 4 or 5 degrees, then it will set the target velocity to 0. If the front side of the pod is facing towards the target, then this if statement will be false and the velocity will just be passed straight into the kinematic equations for the motors. Now this works, but there's another optimization we can do for the pods. let's say our pod's facing up and to the right, and we want to face it to the left like this. We could do what we did in the last slide, which is just turning it counterclockwise like this to reach the target, but it might actually be a lot faster to turn it clockwise like this and actually drive the wheel backwards. This is a lot better because by traveling a short distance, that means it takes less time and less power. And of course, you want to be as efficient as possible, especially in our case where we had 4 Diffie pods. We wanted to be as efficient as possible with the code. On the logic side, doing this basically just adds a little bit to the each if statement. In the section that assigns the R power, we basically just say if the front angle from the target is larger than the back angle from the target. So if the front error is larger than the rear error, then you turn with a pin controller using the rear side. Otherwise, use a pin controller that uses the front side instead. Additionally, we have to modify the actual movement of the wheel part. So in this case, we have an if statement that we added on top that says if the opposite angle from the target is within the margin of error, so if the opposite angle is close enough to the target angle, then to basically just run the wheel at a negative value, so running the wheel backwards. Additionally, we still left in the part where if it's still facing outside of the target or too far out, then it doesn't move at all. So if the front side of the pod is facing the target angle, it's close enough, both of these will still be false, and the velocity will still be equal to the assigned velocity. Okay, and then here's the final pod program from beginning to end. Each step is basically just what I already shown you. I'm not going to go through this very specifically, except this last part is the kinematics or Diffie swerve, which I'll talk about later. So how do you actually tell the motors to move once you have the pod logic solved? For coaxial swerve, it's relatively simple since you have one motor for turning and one motor for running the wheel. You can basically assign the target angle to the turning motor with a PID controller, telling it to move like normal, and then assign the target velocity to the drive motor if the turning motor reads out that it's facing the correct direction. For differential swerve, it's a lot more complicated, and we have to use more inverse kinematics to control each motor individually. So let's dive into that. In the same manner as before with inverse kinematics, we're going to solve it by basically thinking about one dimension of movement and what the pod will have to do to travel in that one dimension. In our case, we have a translation dimension of the pod and a rotation dimension. In the case of moving, we can see that the motors will actually move in opposite directions to make the wheel turn. So we know that when we assign the velocity, one motor will have to be a negative compared to the other motor's velocity assignment. And then in the case of rotation, we can see that both motors will have to turn the same direction. So when we assign the R power, which is again the power we got from the pin controller, that R power will basically be positive for both motors. So here's what the code actually looks like, which is the same as I showed you earlier. The velocity is equal to the wheel movement value, and you'll notice that with the upper motor is assigned as negative because we need one of them to be negative, and in this case, this is just what we chose to have it be driving forwards. And then the R power is going to be our power rotation value, which, as you can see, are both positive. We also have a times power. This is just a modification variable, the same one as earlier that says that allows us to modify if we want to immediately stop or run at half speed. And then the max RPS ticks is there because we use a set velocity method from the DC motor EX, which allows it to use the motor itself to use a PID controller to make sure it's turning at the right velocity. So by multiplying it by the max rotations per second, we convert it from just a 0 to 1 power to a power that can be used by the set velocity method. Okay, so something very important for any swerve drive is that you are able to read the angle of the actual pod. And in terms of coaxial swerve, if you're using a servo, which I personally recommend using a servo for coaxial swerve, then a lot of servos have an internal encoder which you can actually read, such as the Axon Max servo. You're also able to use a separate rev through or a separate encoder like the rev throughbore encoder, but there is an issue in that those encoders aren't absolute, which will be an issue for all of these, which we can talk about later. In the case of differential swerve, what we do is we use more math to basically derive the angle based on the position of the motors, which I'll talk about in the next slide. And then we can also use an external encoder. But for our case, since we had 4 differential swerve pods, we actually ran out of encoder ports. And we could theoretically use an analog encoder like the AnyMark MA3, but those are expensive and not necessarily since you can just do the math. So what is the actual math behind this? When we're going from the angle of the pod to, the position of each motor to the angle of the pod, so the backwards of inverse kinematics, that's called forward kinematics. And explaining how that works with a differential swerve pod is kind of difficult. I would actually fully recommend if you're going to be programming a Diffie swerve drivetrain to actually take a swerve module, in some case maybe a physical one or a CAD model, and just sort of mess around with it and try to get an intuitive understanding of it. And it makes it a lot easier to do things like for kinematics in this case. So what we found when we were actually creating this is that we found that the pod angle is equal to the average position of the both of the motors. This works because in the case of the robot moving just by turning by itself, both motors would turn the same amount. So say both turn like 180 ticks. And then if you average them out, that'll equal 180 ticks for the rotation of the pod. And in the case that they're both moving, since they go in opposite directions, if both of them move like 100 ticks, so one moves a positive 100, the other moves negative 100, averaging that out will still give a value of 0 for the angle of the pod. So solving for the average works out pretty well. Here's what the actual math looks like. Basically, this first part, we solve for the average. Since we only have 2 motors, we do divide by 2. So add them together, divide by 2, get the average. And then we divide it by ticks per degree of the full pod to convert it from a value of ticks from the motor to a actual degree value. You can also do this in radians if you want to. We just prefer using degrees. Lastly, we do angle wrap, which basically takes the degree value we got earlier and says if it's above 180, reduce it down proportionally until it's within the range of negative 180 to positive 180 and vice versa for negative. Angle wrap is generally a super useful thing for both this and a ton of other things in FTC. So if you don't know how that works, I'd recommend searching it up. It's also on Control FTC, I believe. An interesting aspect of differential swerve is that if you want to solve for the position of the wheel rather than the position of the pod itself, you can do almost the exact same equation, but instead of being positive for the average, you do the negative. The way this works is that since both these pods are traveling negative to each other, if you negate 2 values, one which is going to be like positive 100, another is going to be negative 100, negating them will lead to a value of like 200, and then you divide that 2 to get 100 again. So in this case, it works for finding the traversal, and of course for rotation, it does the opposite thing where the values negate each other in a case where it's just rotating. So just going through the code again, it is almost identical to the one shown before. It's just that we have a negative value here for the first part instead of a positive value. And then when we're converting the actual units, instead of dividing by the ticks per degree, we'll divide by ticks per inch for the wheel. This way we can get the amount of inches traveled by the wheel using this equation. Okay, so those are all the things you need to run it. But for the autonomous portion, one of the most important parts of a drivetrain is figuring out how to localize. And if you don't know, localizing just means find the robot's position when you're on the field. If you are able to use Debian odometry, we highly recommend that because it accounts for errors if you hit a game element or if you hit another robot, which can be super useful in more complicated games like this one, where 2 robots might be jousting a lot over shared high goals. But in our case, since we use 4-pod Diffie Swerve, we actually didn't have enough encoders to use Debian odometry. So in our case, what we did for the position is we use Swerve odometry, which we'll show in a second. And then for the heading, we just use the RevHub's internal IMU, which also is basically the gyros to figure out the orientation of the robot. Okay, so how does Swerve odometry work? Before we go into this, I want to give a big thank you to Team 16379 CookieBots because they actually taught me how to do this process and helped me adapt it to our drivetrain. And so credit goes to them for figuring this out. Let's say, for example, the robot is right here and we move to the right. This is a very, very exaggerated case, but I just want to be able to show very easily visually how it works. What we'll be doing is we'll basically be taking the angle and heading of each pod in the beginning, and then where it is after the end when we tell it to update its position. In this case, we can say that the pod ended at 100 degrees as a heading, and it actually traveled 4 inches because it was at 12 and went to 16. Again, not actually accurate to the image at all, but just so that I can show it off basically. If we do this for all 4 pods, we get these 4 vectors that look like this for each pod. And then we're able to take those and average them out to create a net vector, which will be the net change in position. So it'll look like this. This net change in position will actually be equal to how much the robot has traveled since the last time you updated the position. So if you just add this vector to the last known position, you'll get the new position of the robot by the time you call the update method. So how that looks in the code is it looks like this. These parts up here are basically used to solve for velocity, which is a different thing. Then first we solve for the heading of the robot. Then during this for loop, we basically have this value, this accumulator value, which is going to be the accumulated value where we add up all 4 of the different the pod angle and velocity or angles and different distance traveled. So that's what this for loop does. And then at the end, we divide that accumulator by 4, since we have 4 pods, and then use the dot rotate ahead to make it field centric. And then at the end, we return a new post estimate where we do the last position, which is what this is, and we add the accumulator. Something you may have noticed if you're more familiar with FTC libraries is that a lot of these methods, or a lot of these items like the vector 2D and that kind of thing, are actually Roadrunner methods. We didn't use Roadrunner for our robot because we started building the robot during the season and haven't had time to implement that. And we're using Roadrunner is a lot more complicated, which we'll talk about later on. But we basically just created this in Roadrunner with a plan to try using Roadrunner and have been using it for other stuff instead because we haven't had the time to get sort of working with Roadrunner. There is one more method that is very important to do this, which is get delta position. Basically, this returns, instead of just the change in the wheel position on the actual pod, it returns the wheel position as well as the actual angle of the pod, which is what this does. Again, vector.2D is, or vector2D is a Roadrunner class, which we're using for this. It basically takes in the position, so this is how much returned, and then the angle, and converts it into an X and Y coordinate position with the as well as having an angle at the end. So this is pretty useful for that. Oh yeah, again, this is a vector 2D is a Roadrunner variable that represents a 2D vector. Okay, so using those, you should be able to localize now. And with a localizer, you can just do basically normal holomorphic movement. And you're able to use systems like Pursuit for this pretty easily. If you wanted to use something like Roadrunner, it gets more complicated because Roadrunner has a system where it creates trajectories that are reliant on the actual kinematics of the drivetrain that you're running. So with a mechanism or holonomic drive, there's a lot of pre-made stuff that you're able to use to adapt to your own mechanism drive, making it a lot easier to implement. But in our case, since Swerve drive isn't used as often, creating a Roadrunner kinematics class for the Swerve drive is very, very complicated, and we haven't actually done it before. So keep that in mind if you want to try to use Roadrunner, which isn't necessarily necessary, but it's up to you if you want to use that. Here are some additional tips when designing auto programs with a Swerve drive. First of all, you should give the Swerve pods enough time to turn towards the target before telling them to move. In the case of running a teleop, oftentimes you'll give it the angle and then the pods will turn, and some pods will actually reach the target angle before the other ones do, which means they'll start moving first. This isn't necessarily much of an issue in teleop because our human brains are able to account for that error pretty effectively. But in autonomous, you want to get rid of as much error as possible. So it's a lot better to just give the pods time to turn first and then tell them to start moving. Additionally, using Swerve odometry is a lot more stable than traditional odometry since it uses stealth wheels. So it is going to be more effective than using like mechanism wheel odometry, for example, but it still will accumulate error just like any other odometry. So using sensors like distance sensors to relocalize is really helpful in the middle of your autonomous run. Additionally, this goes for teleop and autonomous. If any gear jumps, all of your sensor readouts will be wrong. And this is sort of true for any system in FTC, of course, but it's a really big issue for a Swerve drive, especially differential Swerve, because if a gear jumps under Diffie Swerve, it'll think it's at an angle where it's actually a different angle, facing a different angle, which is, of course, really bad because while the drivetrain starts trying to move, it'll be pushing to the side and going the wrong way and all sorts of issues like that. In the case of a coaxial Swerve, this isn't as much of an issue because you can have an absolute encoder or have the servo to read the position, but it can still be an issue for the position of the wheel. Generally, just try to command your robot with very smooth movements using like acceleration curves, or just not telling it to move like incredibly fast too early. And you should be able to avoid gear jumps fairly often. Also try to avoid going over like really, really rough terrain elements, as they can also mess with the hardware of the gear. But if your hardware for your robot hasn't built fairly well, this might not be as much of an issue to worry about. Okay, that's all we have to talk about for software. Here's some more additional resources, which you'll be able to click on if you go and view this presentation on our website, which will be there later today. Basically, we have our wiki page, which has a bunch of information about everything FTC, including outreach, funding, and later today we'll add in the Swerve webinar as well as other Swerve stuff. We also have the gluten-free Swerve drive, which is just a CAD model. We've learned a lot about how to create a Swerve from theirs, so going on there is a good idea to learn a bit more about it. Additionally, we control FTC, which is that website with a ton of programming resources. Then the FTC lib, which is what we used for actually doing the Swerve kinematics. Then, of course, there's the CAD model for a drivetrain and Swerve pods. Last but certainly not least, if you're coming to Worlds, come and visit us in the pits. We would love to show you our robot and talk with you about how it works and give you tips in there as well. Seeing the robot in person might be a lot easier to understand than seeing it just through a screen. So yeah, come say hi. And also, it's also just fun to meet people. So yeah, that's all we have for the presentation. So let's get started with the questions.
Yeah, so to clarify, that our drivetrain does use all 8 motors. So we have 4 Swerve modules that's in each corner of our robot, and those use 2 motors. And to power our lift, we use 4 Go Build a servos, which powers our linear slides.
There was a question by somebody about whether or not a differential drive is able to use servos for rotation. Because of the fact that differential drive uses 2 motors together to run, as you can see here, if you had one be a servo for they both of the driving things need to basically be the same power. So they both need to be motors in this case, or you could have 2 servos, I guess, but the servos will be a lot slower for moving compared to motors. Just to add on to that.
We got a fantastic question where someone was asking, is the differentiable able to use servos for rotation, or is it only possible for coaxial?
Yeah, that's the one I was just talking about, Jackie.
Right, sorry.
Yeah, just to reiterate in case it was missed, basically a differential swerve drive, both sources of power for the differential swerve have to be equivalent amounts of force for it to be able to turn and move properly, since both of them will be incorporated partially into the movement of the wheel and partially into movement of the pod. So you can use servos, I guess, for both of them, but just make sure that it's the same source, and DC motors are generally a lot better for that kind of thing.
Gotcha. And we also have a question on why we chose the 4-wheel differential instead of the 2-wheel differential.
We decided to use a 4-pod differential swerve because ultimately it's a lot stronger than 2-pod differential, since it uses, of course, 4 more motors. And we thought we'd want to do a lot more defensive plays in this game.
On top of that, we also wanted to try to break into a side of FTC that hasn't been explored very much. We haven't been able to seen any 4-pod differential swerves, so we wanted to also get a chance to experiment it and see how effective it was for FTC, and we found it to be fairly effective. So yeah.
We also have a question: what gear ratio did we use for our motors? And we can also talk about the gear ratio we used for the gears.
So for the motors for our swerve drive, we use Go Build a 312 RPM yellow jackets, and those connect to a 20-tooth gear, and the gear ratio to the rotation of the pod is 20 to 52. But for actually rotating the wheel in the middle, it is 21 to 10. Sorry, it would be 21 to 52 and then 21 to 10.
We have an awesome question. Do you have any resources for designing bevel gears? Most of the resources I have found are excessively technical and difficult to understand.
Yeah, so when I designed the bevel gears for our swerve pod, I essentially used I looked online for many tutorials, such as on YouTube, and there was one really good one. I don't have it on the top of my head right now, but what you do is you essentially use the spur gear plugin to create the profile for the gear tooth, and then Aaron, I think it's a few more slides back.
Okay.
The slide 26, yeah.
Yeah, okay.
And then essentially what you would do with that profile is align it with the diagonal line of the hex with the rectangle. Because what 2 bevel gears essentially are just 2 cones rotating on each other. And to get the length and height of it, you would create a big rectangle, as you can see. And then the distance from one end to the other end is the actual angle of your bevel gear. And you would set the spur gear tooth profile perpendicular to that line, and then use the rotating the circular pattern tool to create all of your gear teeth. Hope that makes sense.
Yeah. Derek, do you think you'd be able to find that video again? Because then if you can, we can post it later on today when we post the presentation and everything. We can post that alongside it.
Yeah, certainly. I can go look for it.
Sure, yeah. And there was a question about where it'll be on our website when it does come up. Just so everybody is aware, we have on the main page, we have a recent development section there. We'll probably be adding it as the most recent development. So when you go to the main homepage, if you scroll down a little bit, it should be there kind of near the top middle area later on.
We got a question in the chat. Do you think 2 modules are enough for a smooth drive? So I know, again, Gluten Free had 2 modules, and Dark Matter also designed one, a Swerve drivetrain using 2 modules. And those worked very well as well. I mean, of course, because you have the 2 modules centered, it's kind of harder to, well, comparatively to the 4-pod module, it is, I guess, less precise in a way.
Yeah, I would say with
I-
a 2-pod swerve drive, it definitely is effective for running just a differential drivetrain in general. The biggest difference probably is that with a 2-pod swerve, you need to have 4 points on the edges, but in this case, they use omni wheels to basically suspend to keep it from like falling forwards and backwards. And in all the cases I've seen, at least of a 2-pod swerve, that means there's a very, very low to the ground barrier on the sides, which with certain games like Freight Frenzy, you might not want that because you'd have to go over the barriers. But maybe in your case, it's fine to have that barrier.
And then there's a
Also-
pretty similar question also talking about having 3 pods instead. So is that kind of the same thing you're expecting?
Yeah, I guess to add on to that, I have seen at least one 3-pod swerve drivetrain FTC, and I believe it was fairly smooth. A thing to keep in mind about triangular shaped robots, which I assume that would be, is that they are fairly tippy if you aren't careful, and so it might actually be good to have omni wheels on it or something so that's low to the ground to keep it from tipping. But 3-pod diffie is definitely a possibility for FTC and not a bad idea at all. Ian, were you going to say something about the 2-pod diffie?
Yeah, I was just gonna mention that how it'll allow you to use dead wheel odometry because it doesn't use all the encoders.
Oh yeah, that is a super useful part about 2-pod swerve. Yeah.
We have a question that is asking, since we used all of our 8 DC motors for our drivetrain, does that limit how much you can do with the game elements? So since our main lift is powered by 4 servos, we're not going to have the fastest lift on the field. It is still able to get up there to the highest junction, but it's not going to be very quick. But I mean, that's the trade-off we planned for in the beginning of the season. We recognize because all of our motors are going into the drivetrain, we'll have to sacrifice a little bit of the effectiveness of how high our lift can go.
Mhm. Yeah, and I will mention that there are some lift designs or different mechanisms that run entirely off of servos. Like I believe certain arm mechanisms or 4-bars, if you design them to be very light, they can be used with just servos. So it may be effective also to try using those ones as lifts, since they can be spring powered, that kind of thing. In our case, we use 4 servos on a lift mechanism, which worked fairly well for us. But yeah.
We have a question. Would Onshape work well for a CAD software, or would you recommend Fusion 360? So one thing we noticed is because Onshape is a on the cloud website software, it is great for making really quick custom parts. But when it comes to actual assemblies, if you have larger things like entire drivetrains that have a little bit more complexities in them, it does take a while to load that up. And I mean, another benefit with both Fusion 360 and Onshape have is the iCloud sharing. So both we can have multiple people working on parts at a time. But we do recommend, if you want to go into mechanical engineering in the future, or any job that requires CAD, we recommend Fusion 360 as that's what's used in the workforce.
I think it's worth mentioning also about Fusion is that you can access it for free if you are a student. If you go to the website, there's probably some section. I know there's some section about like signing up to get a student license for Fusion, which is really nice because then you can get a free license. That's what we've always used. So if you're worried about paying money for Fusion, you do have the option to sign up as a student and actually get access to it for free.
And Fusion can share parts between team members, so it makes it really easy to update in between if you have maybe a part from Aaron and I need it in my assembly. And if you make changes to it, it's a lot easier to keep that updated in Fusion 360 compared to Onshape. And we have another fantastic question. Do you guys recommend making replacement pods that can easily replace a broken pod during competition?
Well, yeah. Wait, do you want to answer or should I answer?
Oh, you can go for it.
Okay. Because each pod is essentially its own separate thing, I do recommend making a replacement, because essentially what you can do is if a pod is broken, you can just take it off from, you can essentially do a hot swap. You can take the broken pod from the drivetrain and then just reinsert the new one. And drive team can use that one during competition while you're busy fixing the broken pod. And whenever you need to, you can always just switch it back in.
There was one thing I want to mention about that is that in our case with the differential swerve drive using 4 motor encoders, that meant that the starting position of the actual encoders didn't read absolute positions. Basically, when you turn on the robot, wherever it started was the 0 position for the pod. So something I forgot to mention earlier was that when we actually start a matchup, we have to use a straight bar and then basically to align the wheels going forwards. In the case of using a coaxial swerve that has an absolute encoder, then if you're going to be hot swapping, you really have to make sure that you're putting it in the right spot with the right orientation, because servos are basically keep their position between matches. So if you pull one off and you have to put it back on, do whatever you can to make sure it's going in at the right orientation, or else when you start running, the wheel will be the wrong angle from what the robot actually thinks it is.
And also with the swapping out, you want to keep in mind that you would need a fifth or additional wheel for that pod, because to try and swap out the wheel in addition to the pod is a lot of extra work. So it'd be easier if you just had the wheel already in there.
We have another question. How do you track the movement of your lift given you only use servos?
So since all of our encoder ports are taken up, we decided to use a potentiometer that is chained to a central axle on our lift. And we had to gear it, I believe, 10 to 40 for the potentiometer, so it's able to properly rotate and not break itself.
See, can you see it on here? Oh, it's kind of hidden, but you can see like back right here is the rev potentiometer. It's basically chained up directly to all of our servos through for just normal rev chains.
There's another question about how smooth is the acceleration to avoid the skipping or slipping of the motors?
Yeah, so on this, doing a smooth acceleration is definitely a software side thing. What we've been using for the most part has been called a moving average filter. It's essentially a filter using statistics that takes in a series of inputs and then smooths it out, so that if you have like an input that's like 0 power and then something 1 power, it'll basically smooth it out to the top by averaging out the current value and the past like 5 values. This has worked fairly well for us, but I would recommend looking into other options for acceleration curves, because that was sort of a the moving average filter works, but it isn't perfect. There are some limitations in terms of like you can't use it in the first few updates in a match, and using it for auto has been difficult to implement. So especially for autonomous, I'd recommend looking into how like trapezoidal acceleration curves, which you can actually view on Control FEC as well.
So we do have a couple of questions regarding like our in-game performance, since all of our 8 motors are taken up. So we have, how does your robot perform in-game without motors for the lifts? We also have one stating like what linear slides we use, and the if our lift is faster since we're using the super speed servos. So a lot of our team has done well in performance, as we were selected for Final Alliance, and although we're not able to score as fast, one of the things we do utilize is strategy, where you're placing the cones. And like, we personally, our team, we go for a circuit during endgame to help with that. But because we're very maneuverable around the field, so we like to play towards the opposite alliance's end to try to own those cones. The linear slides we use are the Misumi telescopic slides. And there are also other options available out there. I know if I recall, Go Builda has their own Viper slides as well. But our team, we chose to use Misumi, as they are both very fast and durable, and very solid when they're fully extended.
Yeah, I think it's also worth mentioning that when we were stringing up our lift, we intentionally chose to do a cascading lift system, which I recommend searching up. Basically, it's a way of rating lift so that all the slides extend at the same time, which runs a lot faster. In the case of using servos or any sort of slower motor, by figuring out the kind of rigging you use for your slides, that can make them run a lot faster, which has definitely helped our robot in terms of speed. But as Jackie mentioned, we don't always go for the high goals that often, so we didn't necessarily need to be a super fast lifting robot.
There was another question about the plastic to plastic interfaces on a robot, and wondering if those cause any issues with friction or wear.
So for a majority of our plastic interfaces, those are going to be with PETG to nylon or nylon to nylon. And since nylon is a very low friction material, there isn't that much wear there. And we do also apply silicone grease to the parts where there would be excessive wear to make it even more low friction. So it hasn't really been an issue.
There's also a question about using servos for a drivetrain, which I would like to reiterate on. So they did ask about CookieBot's uses method. I do believe CookieBots has a setup called, which is the coaxial swerve, which is the one that looks like this, where it has one motor basically turning the pod and one running the pod. In their case, what they have is they have one DC motor that actually turns the wheel itself, and then the turning of the pod is done by, I think you're right about it being a super speed servo. Turning the pod might actually be faster than ours, because in our case, DC motors are fast, but using a super speed servo could be faster. It's just that the reason we didn't go with coaxial instead was because it would have less power generally, in terms of less pushing power and less defense when running around. Coding wise, I'm using a coaxial drivetrain. I didn't go over a whole lot, but basically, instead of doing the kinematics what we did for controlling a differential swerve pod, the only difference would be that let's see, where is it? The only difference would be that, okay, oh wait, here it is. Yeah, so no, that isn't, never mind. The only difference would be that in the case of a coaxial swerve, you basically just assign the direction to one motor and assign the power to the other motor. So everything up until the actual pods themselves is exactly the same for coaxial and swerve. It's just that final step of assigning the motor speed and the pod angle to the motor, basically giving the motors commands, is going to be different. Additionally, taking in inputs like how far the wheels travel and that kind of thing will also be different, but it's not going to be more complicated than differential swerve to code.
We have a quick question. How does SolidWorks compare to Fusion 360? So our team, we personally don't have any experience with with SolidWorks. We know that there in the FTC community, lots of teams prefer, there's a huge debate between SolidWorks and Fusion 360. Our team likes Fusion 360 because of being able to cloud share and how easy it is to update parts that are made by different people. But we don't have much experience in SolidWorks.
If you are planning on going to like engineering or another CAD focused industry, I would actually recommend using SolidWorks to Fusion 360, because the vast majority of companies are going to be using SolidWorks. That's also what's going to be taught in college.
And we also have, what manufacturing process do you use for making custom parts? I mean, Ian and Derek, do you guys want to talk about that?
Yeah, okay, so for all the purple and orange parts, those are 3D printed parts from PLA, PTG, or TPU. We make those in-house, as we have our own 3D printers for that. For the nylon gears, those were printed by Stratasys using a powder technique, which has 100% infill, which increases the strength of the gears. And for our base plate, that is custom cut by a company called Conquest.
This is a good question. You mentioned that you knew all the risks you were exposed since you used all the motors for the drivetrain. Do you think about using Mechnum in the future, or building a coaxial swerve, which would give you extra motors for the system used? So I think after our second qualifier, this is when we first used our swerve drive to compete. And we were trying to think about our state tournament. It's like, do we want to go back to our Mechnum drivetrain that we used during the qualifier 1, or do we want to stick with the swerve? And although we did score better using the Mechnum drivetrain, I think we stuck to swerve because it was a concept so cool, and we want to bring it to World Championship and show like there are other options out there that aren't Mechnum drivetrains that you can still score effectively with.
Yeah. The conversation was interesting because we knew for sure that running Mechnum drive would be a lot easier to do, a lot easier to score well with that. Especially since during the qual 1, our very first match in qual 1, we actually scored probably the best we've ever had in FTC at all, which was a lot of fun. But we knew that the point of FTC is to learn and to do new things. We've done Mechnum so many years that we know how to do it pretty effectively. And so we chose to do Swerve partially because it's innovative and something that we don't know how to do, and it's something we want to learn about how to do. So we got a lot more experience through doing Diffie Swerve than we would have done through just going with Mechnum. And this is our last year in FTC. All of our members are graduating, unfortunately. going in the future, I think that we will probably choose based on our goal of either being more innovative or being more competitive. Though being more innovative in a sense and working for a differential swerve drive is something I definitely would be interested in going forwards if I had the time.
How many iterations of this design did your team go through? So iterations of the Swerve pod, I do not know the number off the top of my head, but we went through lots of different, I mean, individual, you can talk about it, Ian.
Yep. So for the Swerve pod and Swerve Drivetrain as a whole, there are essentially 4 distinct iterations. The first one was essentially a prototype of the concept. So it was just the pod itself with the two upper and lower gears, and then the bevel gear and the wheel, just to make sure the concept works and so that we can better understand it. Next one was a prototype of the full module, but it used thrust bearings. And the thrust bearings we had weren't the biggest weren't that big. They were only 12 millimeters in diameter, and this led to a lot of instability. So we eventually switched to using needle bearings, which worked a lot better, but we did decide in our final design to add supports onto the upper gears to make it even more stable.
Okay, there was another question about using field-centric navigation for this. In terms of the autonomous period, we always have used field-centric, and the actual odometry system that I showed off earlier does use field-centric stuff through finding the angle and modifying it based off of that. In terms of the Teliac period, we actually attempted to implement field-centric mode for, I believe it was Qual 2, we used it. And we found a really interesting problem that comes up with Swerve that wouldn't come up with other drivetrains. So when a Swerve drive is basically running, if you're running with field-centric mode and you tell it to start turning and moving at the same time, it'll actually start drifting to the side. So let's say I'm inputting straight upwards, the robot will actually, and I'm turning to the left, the robot will actually like drift to the side like this, or drift to the other side like that. This is a problem that has existed not only just because of the Rev hardware and FEC, it's actually a problem that has existed in FRC as well. And as far as I'm aware, we couldn't find any solution for it. Actually, it's been an issue for some time, and the closest solution we could find was one that I will post later when we do post a presentation. Anything else, I'll add it to it. In terms of using field-centric drift, which involved basically reading the current velocity and setting a target velocity for the robot. But because this field was so specific and it has such small channels the robot has to pass through, using a field-centric drive that caused that drift side to side made it very, very difficult to control. So currently we're using robot-centric. If we were able to solve the issue, we probably would switch to field-centric because that'll make it a lot smoother in terms of scoring and stuff. But if you do try field-centric with Swerve, keep in mind it is not easy to do, and that issue is very persistent. And so again, we'll post that paper we found about how to solve it or how to kind of solve it online along with the presentation. In terms of just implementing it, though, it is practically the same. It's to just put in. It's just that one issue shows up that makes it a lot more difficult to use. Just to clarify. Okay. Do we have any other questions we haven't answered yet?
And I mean, if you guys do have questions later on, you can contact us through our team email, the one that was used to send all the Zoom webinar information, or you can contact us through Instagram, Twitter, or Facebook.
Yeah.
Yeah, and again, the recording and the webinar slides will be available on our website after this later, and yeah.
Yeah. Also, we did mention earlier that this is our last year we're graduating, but I would say, at least for me, and I think a lot of our team members, we are willing to help out during the summer and beyond, you know, after we graduate from FEC. So if you have any questions, contact us through the same manner, or if you see us on the FTC Discord, maybe you can DM us there as well if you want. Yeah, thanks for coming, everybody.
Yeah, I mean, we still got a couple of questions.
Yeah, oh, yeah, sorry, more questions? Okay. Yeah, sorry. I got excited. Yeah.
Yeah, so one of them was wondering about why we needed 2 thrust bearings on top of the module. So if you want to go into that.
Yeah, so if you can look at that cross section, because the way how the bolt clamps the Swerve module to the drivetrain. Yeah, that diagram still works. Yeah.
Sorry, I'm trying to turn on this thing. It messed up the slide, but yeah.
Yeah, you see that there's going to be force acting on the top and bottom. So that means that you'll need 2 thrust bearings, one for the top plate and one from the bottom. And this makes sure that no parts are scraping against the actual base plate itself, and they are isolated.
There's also a question about asking about what happened to the gluten-free Swerve drive. So gluten-free is was an incredible team from a couple years ago. They actually ended up graduating, I think, after Skystone, which was the game 3 years ago, something like that.
Yes.
And they created a Swerve drivetrain during that season, but I believe that they never really planned on implementing it, or at least they didn't think it was competitive for the game. Or it might have been that it was just too late and they had graduated by the time they had finished building it. I'm not exactly sure about that, but there are videos online of showing that drivetrain running around, and they did actually use it on a off-season robot they had that was a ball launcher robot. So if you search up gluten-free Swerve drive on YouTube, you can find some really good videos of their 2-pod Swerve drive running around and doing things, basically. Yeah.
We have another question. I've seen Swerve robots in FTC done before with only 2 pods. What was the reason you guys chose 4? Well, not first of all, when we have 4 pods, that means we have 8 motors. So all of that force means that we'll have a very strong pushing robot, which ties a little bit into our team field strategy. And I mean, someone else can continue on with why
Sure.
we chose 4.
So
Also,
yeah.
yeah.
Yeah, did go for it. Go crazy.
Okay. Also, like on the hardware side of things, if you can go to the gluten-free Swerve drive, slide 31st. Yeah, 31.
Shoot, wait, okay. Got it. Nope, that's not
No,
34.
31.
31.
You just-
I see. There you go.
There you go.
Yeah. Okay. So because in this game there are ground junctions, it means that the robot has to like climb it or overcome them. With gluten-free's like 2 swerve design, if a corner gets lifted, that means that one of the swerve modules will not make any contact with the floor, and you're basically stranded on the field. And another thing with power, another thing with is the ground clearance, but that's just due to mounting. With 2 pods, you have to have a bunch of, I guess, dead wheels on either sides. And what that can introduce is your robot will get very close to the ground. And that's also very inconvenient if you try to go over a ground junction for this season anyway.
Yeah. Adding on to the game strategy piece, our goal for this year was basically just to be a really aggressive roamer bot that can go from A to B really effectively and quickly and basically push other bots out of the way if we're trying to get to a specific junction of certain sorts. So by having 4 pods where we were able to go over ground junctions very smoothly, we were able to push other robots out of the way if they're in the way, and also prevent scoring. And even with like AFK bots, the ones that kind of sit in one spot, we can just push them out of that spot, so they have to readjust, that kind of thing. So having 4 pods ensured that no matter what, we would be the most powerful robot on the field.
We have another fantastic question. Do you have any other resources that you would recommend for our team to look at? So other than Stratasys, which I know will help out teams regarding 3D printing, look for local metal shops. So maybe they're like sheet metal manufacturing, or people or companies that do work with sheet metal. That's how we're able to get our drive-based laser cut, and they have helped us in the past with various other robot parts. I'm trying to think of another one. Maybe a company that specializes in wiring. So if you want any advice on how to wire robots, because we all know how that goes sometimes, that would also be a great resource.
Yeah. One more resource I would like to add is that strangely for Swerve, it actually is a good idea to look at Chief Delphi, which is the FRC forums essentially. The reason I recommend that you look into that is that Swerve is a lot more common in FRC. Even though it is mostly coaxial Swerve, there are still some differential Swerve instances in FRC. And so if you're having difficulty with the software side or hardware side of your Swerve drive, it might be good to look on the FRC subreddit or looking at Chief Delphi and asking there for advice, because those teams have a lot more experience with Swerve. Their robots might be a lot bigger, but we're both building robots. So either way, they can help you a lot in terms of developing a Swerve drive like this.
Other additional resources, you can always check out Project Robotica. Game Manual 0 is also a fantastic resource. The FTC Discord, there's always people on there. It's always very active. You can always shoot in a question, and you'll usually get a response within 24 hours, if I recall. Yeah, Reddit, again, fantastic resource. And just local teams. I know, although some teams may be retired, some of their alumni still may be active in the community, so it doesn't hurt to shoot out an email to them.
Also, depending on the type of team, there's a lot of teams that I found that don't necessarily ask for a whole lot of advice from professional engineers, and I highly recommend going to the engineering companies around you. One good way of finding them is you could just search them up, like local engineering companies, or just driving around your area. And if you see any company that has a cool name, like fabrication company, blah blah blah, whatever, like search them up later. And then if they seem like a cool company that can help you out, like actually call them up and say, hey, we do high school robotics, and we want to talk to you about getting help with our robot, and also maybe you can demo to them as well. So that helps with outreach as well. Doing those kinds of engineering demos and also just talking to engineers is super helpful for all the stuff, because they know a lot of stuff that's difficult for us to find since we haven't gone through the college experience of learning college level robotic stuff. So a great resource is professionals who are currently doing this as their job.
Yeah. Another great question. What should a team who'd like to build a Swerve pod with barely any experience in FTC do? So again, if it depends on how much time your team is willing to put into this, because our team did not work on this during the off season. This took a lot of time during the season, not only developing the drivetrain we needed to compete with, but also alongside the Swerve. So we were kind of making two robots at the same time, essentially. And it depends on your resources. Do you have enough people? Are you willing to put in the time commitment? And Ian, would you like to talk more about it?
So first off, if you have barely any experience in FTC, I'd recommend focusing on simpler drivetrains first, like Magnum Drive, because this does require a lot of extensive experience in CAD to create all the custom parts that are necessary to make it. But if you do want to start looking into it, I'd recommend looking at both our Swerve Drive, KookieBot's Swerve Drive, they have a CAD posted of it, I'm not sure if they do, and Gluten-Free Swerve Drive to better understand how it works, and start from there with little steps by making a conceptual Swerve pod first, and then working up from there.
Also, no matter what you do, always follow the engineering process. This prototype, test, find this issues, prototype again, which of course will take a lot of time. So yeah, I personally would agree with Ian. As a software person on the team, I would recommend that if you want to build a Swerve drive, hold off on it for the first season, or at least dedicate a lot of time over the summer or off season to building a prototype one, because it is very complicated. And on the software side, it's probably one of the most challenging things I've done in terms of software, and I've been programming for 9 years now, including my Lego League era. But yeah, so if you're gonna be if you want to build Swerve, get as much experience as first with simpler systems that are more effective, because one of the most fun parts about FTC is competing well. And if you have a really cool robot that is awesome in theory, but doesn't perform as well as it could, then it might be a lot more draining to go to tournaments and end up performing poorly. So I'd recommend for sure getting more practice making with optimizing drivetrains that are less intensive to create and program.
Yeah, I do want to mention though that with the challenge, that there's so much learning. When our team
Yeah.
developed these, we learned so many things that we probably wouldn't have learned if we just stuck with a simple Mechnum drive. So I mean, with the challenge comes great growth.
Yeah, big challenge, big growth. Oh yeah.
Alrighty, another question is: aside from being innovative and unique, is it worth it performance-wise? Does it give a significant advantage in the robot game? What is your opinion on that?
Okay, so I would argue that this is a drivetrain like Mechanim Drive is a very general drive that's good for a lot of different games. Basically, any game Mechanim is good at. Well, in terms of Swerve Drive, it's a much more specific drive that is only good for a handful of specific games. So if you're going into a game like Ultimate Goal, that kind of thing, if that game was not COVID and Ultimate Goal was in person, Swerve Drive might have actually been a really, really good option, because in that case, being able to push other teams out of the way to get access to the rings and also mess up their shooting would have been very, very effective thing to do in terms of playing defense, right? But with a game like the one this year, we chose a Swerve Drive kind of because it's our last chance to be able to, and we wanted to be innovative. But building a Swerve Drive for a game like this year, where scoring takes a lot of precision and also traveling down the lane takes a lot of precision, building a Swerve Drive may not be worth the performance. The benefits may not be worth the difficulty of creating one that's super, super consistent. So I'd recommend looking at the game, more open fields with less things in the way. I definitely would recommend going for Swerve, or at least trying it out. But in a game where there's more things on the ground or driving around requires a ton more precision, it might be better to go with something else, just because it's gonna be less complicated to make it work as effectively as a Micro Drive.
I mean, there's also the counter argument is because the Swerve drivetrain, although it can't, I mean, it's not as precise minuscule movements you can do,
Many
it's still
movements, yeah.
beneficial, like with the rows and lanes, because all the wheels will turn at the same time, and you can dart like strafe to the other side of the field. Which sometimes mechnum strafing can be a little iffy. It's very difficult to maintain a like straight strafe. Oh wow, that was a little silly. If you have maybe like an unbalanced robot, for example.
Well, actually, as the person, as somebody who's been programming with and did both Mechanum and Swerve this year, I would definitely agree that Swerve has the potential to be much more effective than Mechanum, but Mechanum was a lot less complicated to get right. Since Mechanum is like velocity based, it has that drifting or where it can like slide. It made it very easy to do minute adjustments in terms of driving, and using a PID controller to control the movement of a Mechanum drive in teleop and auto was less complicated to do and figure out. Swerve drive would definitely be more rigid, but you have to make sure that you're traveling exactly vertically in this game. And doing that wasn't easy. It was definitely good in terms of learning. And once we had it down, and now we kind of do, it was really fun at working and is working very well for us. But it will not be easy, is the thing. So that's something to take into consideration.
That was a great question, though.
Yeah.
So thanks for asking that.
Any other questions people have? If you think of them later, again, please email us, let us know. Seems like we have one more
Sure.
here.
So this question was asking, would you say Swerve odometry is as good as Mechanum dead wheel odometry? No matter what drivetrain you do, dead wheel odometry or some sort of tracking that doesn't rely on the motors is going to be better, basically just flat, because if you have a Swerve drive like ours, you're driving along and suddenly you collide with another robot in auto. If you have dead wheel odometry, then you'll be able to correct for that. Your robot will know that it didn't like keep driving to the side, or if you're pushing against something. But with ours, if we do that and a robot keeps pushing, sure, we'll push them to the other side of the field, which would be kind of funny to watch. But at the same time, our robot won't really know where it is because it's pushing and not traveling as far as it thinks it does. So Swerve odometry is not as good as dead wheel, but it still is very effective in the absence of odometry. And if you do go with a coaxial drive or you go with a 2-pod differential, you have the option for dead wheel odometry still, which I would highly recommend fitting under your robot somewhere if you can. It is also worth mentioning, though, that dead wheel odometry isn't the only way to localize outside of motor encoder odometry. Options like VI Slam, which was a webcam you could use to detect movement of the robot, seems to be fairly effective. I haven't used it myself, but I've heard it's good. Additionally, using cameras to recognize the side images is fairly effective. And in the game like this year, you can use the distance sensors to detect the junctions, which is a good way to keep track of where the robot is in case there is some sort of slippage. So generally, depending on the game, where odometry might not always be completely necessary if you are smart about paying attention to what you can use out of the game.
Got another question. Can a 2-module do a 360? Yes.
Yes. So going back to the kinematics of the 4-pod Swerve drive, let's see. I think that's like this one. Yeah, this one kind of works. The actual, for any drivetrain of any layout with any amount of pods, the X and Y inputs will always be identical. Actually, let's go to this one's probably better to look at. The X and Y inputs will always be the same, because if you imagine a Swerve drivetrain just moving in one direction without turning, all 4 pods have to face the same direction. That also applies for a 2-pod Swerve, 3-pod Swerve, etc. The only difference a 2-pod Swerve will have is that these the red arrows here, which are the rotation powers, they're going to be facing a different direction. And if they're right next to each other, they're actually, one's going to be going straight upwards and one will go straight downwards. This is because if you imagine a 2-pod drive just spinning in place, which is definitely possible, one pod will be facing up. Well, the other one's they're both facing the same direction. It's just one will be moving backwards while the other one moves forwards. So 2-pod Swerve has the same amount of movements it can do as 4-pod. The difference is in how much power it has in that movement and how stable it might be.
That's a good question. And I mean, if you guys have any other questions about, honestly, anything like 3D printing, robot making,
Outreach,
we could do that.
EP,
Video, pit design,
pit design,
making a website. We have, it's our last year in the program, and we're trying to, I guess, share as much as possible with everyone in our community. And that's why one of the resources we created was Project Robotica, because our team's graduating. We want, as much knowledge that we learned to be available for everyone. And not only that, Project Robotica allows other teams to contribute their information too. So if you're interested, maybe you want to include your engineering portfolio so other teams can see it. that'd be fantastic. If you want to do that, please reach out to us. We can help you make a account, and you guys can, I mean, you can write about anything. If you want to write about the basics of 3D printing, maybe odometry, or maybe smaller, like more niche systems, like how to design a robot with cool acrylic, or how to do LEDs, because that is really cool. I think that's something our team's still trying to try.
Mhm.
Even if you do have FRC and FLL experience too, we would love to hear um, what you guys have learned and experienced, and if we can get that written down just for more people to learn, that would be fantastic.
There was another question about whether or not we recommend 2-wheel or 4-wheel swerve. I think that it just heavily depends on the type of game, and if you choose coaxial versus differential swerve. 2-wheel, basically the best option for 2-wheel is differential in any case. And I say that 2-wheel swerve is a pretty effective design, especially in games that don't have any sort of terrain elements, or like again, like Ultimate Goal, where the field was completely fat, or even Skystone, if you're not going to go over the center like jump thing, then it's probably a good idea to use 2-pod swerve. If you're going to go with coaxial, I'd say 4-pod is probably the best because it gives you a relatively similar amount of power with a 2-pod as well, while also having a lot of ground clearance with the coaxial swerve. But 4-pod different swerve is also a really good option if you're doing 4. I'd say it just depends heavily on the game type, really. Ian, do you have any suggestions since you're more of a harbor?
Not that I can think off the top of my head, sorry.
Yeah, you're fine, yeah. Yeah, basically just look at the game and see if you need that ground clearance and see if you have certain tasks that require the motors. Like this year, we didn't need motors really for scoring. I mean, like motors would make it a lot faster, sure, but we didn't necessarily need that speed. But with a game like Ultimate Goal, you have launchers that use flywheels to actually spin it up, and doing flywheels with servos is not something that I think would be like realistic, or at least not easy. So if the game has scoring in the game would be a lot more efficient with motors, maybe go with a 2-pod or go with coaxial, that kind of thing.
A great question. We have you been to Worlds? So do you have any tips for the pits? So our team hasn't actually competed at Worlds, though last year we did have some members, watching the competition, which was fantastic, by the way. But one thing we did notice as we were walking around the pits, I mean, it really varied. And transportation, when you're transporting stuff, you don't want to, you can't fit a lot on an airplane or in a car. So definitely try to capture your team spirit, but you don't need to go overkill with like a massive foam castle, for example. We've seen teams do those little pop-up tents that you have like graduation parties, for example. So I've seen teams string little LEDs or even little rubber duckies on the inside. But I mean, you got to keep in mind how much you want to pack because you're transporting this stuff. It depends on where you're from. Maybe if you're actually in Houston, maybe you could go a little more all out with the pits. We actually do have a pit design page on Project Robotica that goes a little bit more in detail about that. So if you want to check that out, go right ahead.
Yeah, this is our first year going to Worlds, and because of that, we've been trying to go through that process of like designing a pit that has been very simple to transport. And so a lot of our actual things that we have gotten with us or bring with us are like certain banners that can deploy really large but are really compressible. Like the back of our pit is going to be one large backdrop that is just a piece of cloth that has a bunch of supports on it. So I definitely recommend looking up at deployable banners and that kind of thing, things that don't take a lot of space in transporting but it can be deployed to be very large because those are super useful. Also, if you're having a pit, make sure there is, or in your pit design, make sure there is space to walk around and to work on the robot, but also make sure that if somebody's walking up to the pit, that they don't feel that they feel like they can approach you and talk to you, because you want to make sure that judges have very accessibility to the back as well as, or just to the team basically.
Alrighty, we got another question. When you've used odometry pods, did you design or build your own? If so, what are good resources to learn more? So in the past, our team has actually designed our own odometry pods, but I mean, with odometry pods, there are so many resources out there. I've seen, if you go to Game Manual 0, they have a very intricate page that talks about different dead wheel designs. We also have a page, if I recall, about odometry programming and design on our Project Robotica. But one of the things we kept in mind was that if you want to design your own odometry pod, you have feel free to. There are lots of compact designs that have been remixed over and over again, so they've been refined over times. And the one thing we do stress is spring-loaded odometry. Even if a field doesn't have any like bumps or whatever, there's still, the maybe imperfections, and there's more accuracy when it comes to the spring-loaded dead wheel odometry.
Yeah, when it comes to dead wheel odometry, it's a very commonly used system by a lot of the higher up teams. And so because of that, if you go to a place like Reddit or Discord and you ask questions there, you will get a ton of really good help with that. Also, you can just search up like in the search bar, like odometry. Things in the past will show up a ton of examples of ways teams have designed them, as well as tips they have for that and how to use them in software. So since it's so common, I definitely recommend looking into the community directly with like Reddit and the Discord and asking there for help, because there'll be a ton of people who would be glad to help you.
There was also a question about do we have tips for sponsorship and getting access to like CNC services. So I think Aaron mentioned earlier, but one thing we did was we kind of looked around in our local community and found some of those, small engineering companies, different things like that. And we ended up just cold calling and cold emailing a whole bunch of them. It seems pretty scary, but it's not too bad. And we were actually able to find quite a few good sponsors there. And we've created some lasting relationships with some of them. Some of our members even getting like internships at a few of the companies over the summer. And so you can get sponsorship as well as just help from the engineers. That's another great way to get engineering outreach, by making those connections.
Yeah. When actually going and approaching a company like this, just to clarify, cold calling and cold emailing is basically just emailing or calling them out of the blue, kind of. Like in our case, when we called somebody, we would say, hey, we're a high school robotics team and we want to talk to you about demoing our stuff, or talking about either funding or in-kind donations. In-kind donations meaning like things that they would make for you. So if there's a company that does like manufacturing, in-kind donations would be like them manufacturing parts for you. As for getting access to CNC services, if your school doesn't have one, then one of the best options we had that didn't involve going to a company was a local makerspace called the Hack Factory. It's essentially just a building that has a ton of manufacturing like tools that are free to use as long as you sign up for it and like volunteer to help out, that kind of thing, I think. And in our case, that one actually offered free membership for FTC teams and stuff. So I'd recommend searching up like local makerspace companies, that kind of thing, and you might be able to find some that are available, and then you can cold call them, ask them if you can get membership for free, that kind of thing, if they're ability to support you. And also, of course, there's the option of going to companies that have CNC machines, but those might be a little more difficult to access on repetition, that kind of thing.
And I mean, if you really want to, one of our friends, Armored Artemises, they actually created their own CNC machine, if I recall correctly, which was crazy. And if you do a lot of CNCing and you think it's worth the investment, go for it.
Yeah, having an at-home CNC machine will be a lot more convenient than going somewhere else for it every time, but it isn't cheap, of course. So take that as you will.
Yeah. Alrighty. Do we have any more questions, concerns, comments? Questions?
Well, thank you all so much for coming to our webinar. We hope you learned something and enjoyed it. And again, if you have any more questions you think of later, please email us. We'd be happy to talk with you more.
Yeah, you guys asked some awesome questions, by the way, and you guys made it a lot of fun. So thanks to you guys for listening in.
Yeah, no, it was a lot of fun. Yeah. Feel free to contact us also through like Discord or whatever, if you see us on Reddit, that kind of thing. Sorry for those of my teammates who don't want that, but honestly, like me personally, I love being contacted by teams like that. So any questions at all, literally anything, or just want to say hi, then for sure do it.
Oh my god, yes. Also stop by our pit. We want to meet you guys because you guys are so cool.
Visit us at Worlds.
Or watch our YouTube. Or follow us on Instagram, Twitter, and Facebook.
Subscribe on YouTube, like our videos.
Like our videos. We don't have a TikTok. And I think we're keeping it that way. No, we're keeping it that way.
Yeah. This is laughing and crying emojis. What the heck?
It could have been the Easter Island head emoji.
the moi.
The moi.
The moi.
Alrighty. SpawnCon signing out.
Yeah, how do we stop the stream though? Is that a thing we can do?